Next, our portion is molecular orbital theory. MOT, molecular orbital theory. This theory was developed by F. Hunt and R.S. Mulliken in 1932. The important features of this theory are: in the case of atoms, the electrons are present in the atomic orbitals. Similarly, in the case of molecules, the electrons are present in the molecular orbitals. The atomic orbitals combine to form molecular orbitals. The electrons of atomic orbital is influenced by one nucleus, but the electrons of molecular orbital is influenced by two or more than two nuclei. Next point, when two atomic orbitals combine to form two molecular orbitals, one is bonding molecular orbital and other is anti-bonding molecular orbitals. So, when two atomic orbitals combine, then we get two molecular orbitals. One is known as bonding molecular orbital and the other one is known as anti-bonding molecular orbitals. The bonding molecular orbital has lower energy and greater stability than anti-bonding molecular orbitals. That means the anti-bonding molecular orbitals have higher energy and less stability compared to bonding molecular orbitals. In the case of atoms, the probability of finding electrons around the nucleus is known as atomic orbitals. Similarly, in the case of molecules, it is known as molecular orbitals. You know, in the case of atoms, the probability of finding electrons around the nucleus, that space is known as orbital. Then similarly, in the case of molecules, the probability of finding electrons around the nucleus is known as molecular orbitals. The electrons are filled in the molecular orbitals similar to that of atomic orbitals based on Aufbau principle, Pauli's exclusion principle and Hund's rule. You know, atomic orbitals, the electrons are filled on the basis of these Aufbau principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity. Similarly, the molecular orbitals also filled based on these principles. Next, types of molecular orbitals. You know, the atomic orbitals combine to form molecular orbitals. Then these molecular orbitals are of two types. First one, sigma molecular orbitals. You know, sigma bond is formed by the axial overlapping of atomic orbitals. Similarly, these are formed by the axial overlap or head-on overlap of atomic orbitals. That molecular orbitals are known as sigma molecular orbitals. The next one is pi molecular orbitals. These are formed by the lateral or sidewise overlap of atomic orbitals. So, these are formed by the lateral or sidewise overlap of atomic orbitals. So, on the basis of this Aufbau principle, Hund's rule, Pauli's exclusion principle, the filling of electrons in the molecular orbitals in the order, as the increasing order of the energy of these molecular orbitals are sigma 1s less than sigma star 1s, which is less than sigma 2s, which is less than sigma star 2s, which is less than pi 2px is equal to pi 2py. That is 2px and 2py having same energy, that is formed by the sidewise overlapping. So, it is known as pi 2px is equal to pi 2py, which is less than sigma 2pz, which is less than pi star 2px, which is equal to pi star 2py, which is less than sigma star 2pz. So, this is the increasing order of filling of electrons in the molecular orbitals. We can fill the electrons in these molecular orbitals. But one exception is there. For oxygen and fluorine molecule, the order of filling of electron is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then sigma 2pz is slightly less energy in the case of oxygen and fluorine compared to pi 2px is equal to pi 2py. So the sigma 2pz coming first, then which is less than pi 2px is equal to pi 2py, which is less than pi star 2px is equal to pi star 2py, which is less than sigma star 2pz. Then we can fill the electrons in this molecular orbitals, that is electronic configuration. Electronic configuration, you know what do you mean by electronic configuration? Yes, the distribution of electrons among various molecular orbitals is called electronic configuration of the molecule. From the electronic configuration, we can identify the following aspects. First one, stability of molecules. We consider Nb is the number of electrons occupying bonding molecular orbitals and Na is the number of electrons present in anti-bonding molecular orbitals. Nb is the number of electrons present in bonding molecular orbital and Na is the number of electrons present in anti-bonding molecular orbitals. Then Nb is greater than Na, then the molecule is stable. That is, the number of electrons in bonding molecular orbital is more than that present in the anti-bonding molecular orbital, then the molecule is stable. Then, Na is greater than Nb, that is, number of electrons present in the anti-bonding molecular orbital is greater than that of bonding molecular orbital, then the molecule is unstable. Then next, we can find out the bond order from the electronic configuration. Bond order is defined as the half of the difference between the number of electrons present in the bonding molecular orbital to the number of electrons present in the anti-bonding molecular orbitals. That is, we can written as half into Nb minus Na. Nb is the number of electrons in bonding molecular orbital, Na is the number of electrons in anti-bonding molecular orbitals. Then a positive bond order, which means Nb is greater than Na, which means the molecule is stable. While a negative bond order, that means Nb is less than Na, or the bond order is 0, which means the molecule is unstable. When the bond order increases, then the bond length decreases and the stability of molecule increases. Next, magnetic nature. From the electronic configuration, we can identify the molecule is paramagnetic or diamagnetic. If all the molecular orbitals are doubly occupied or paired, then the substance is diamagnetic. When all the electrons are paired in the molecular orbitals, then the substance is diamagnetic. Diamagnetic means substances which are repelled by the magnetic field. Diamagnetic substances which are repelled by the magnetic field. However, if one or more orbitals are singly occupied, that means unpaired electrons occupied in the molecular orbitals, which is paramagnetic. Paramagnetic means substances which are attracted by the magnetic field. So, due to the presence of unpaired electron, the molecule exists as paramagnetic material, and due to the presence of paired electrons, the molecule exists as diamagnetic materials. Paramagnetic means attracted by the magnetic field, and diamagnetic means repelled by the magnetic field. So, from the electronic configuration of this corresponding molecules, we can find out the stability of molecules, bond order, then magnetic nature of the molecules. Then we can now discuss about the bonding in some homonuclear diatomic molecules from the electronic configuration. First, we find out molecular orbital electronic configuration of hydrogen molecule. You know hydrogen atom, atomic number 1. So, here 2 hydrogen atoms are there. So, total number of electrons 2. Total 2 electrons are present, 1 hydrogen 1 electron plus other hydrogen 1 electron. So, total 1 plus 1 2 electrons. Then the electronic configuration is sigma 1s. Then the bond order, you know, half of the difference between the number of bonding molecular orbitals and the number of anti-bonding molecular orbitals, that is half into Nb minus Na or Nb minus Na by 2. Then here the number of bonding molecular orbitals can be identified. There is sigma is only present. If there is a star is there, then this is anti-bonding molecular orbital. Sigma 1s is bonding molecular orbital, sigma star 1s is anti-bonding molecular orbital. So easily we can identify star is there, then it is anti-bonding molecular orbital. Here there is no star with the electron in molecular orbital, so here only the number of bonding molecular orbital electrons are 2. 2 electrons are present. This is a bonding molecular orbital, so 2 minus, there is no anti-bonding molecular orbital, so 0 by 2, which is equal to 1. This means 2 hydrogen atoms are bonded together by a single covalent bond. Bond order 1 means, you know, bond order is defined as you previously studied. The bond order is defined as the number of bonds present between atoms in a molecule. So here bond order 1 means in between hydrogen atoms a single bond is present. Since here no unpaired electron present in hydrogen molecule, that means only the electron is pair up in the molecular orbital 2. That is paired electron. So this is diamagnetic in nature. The electrons are paired in the molecular orbital, then this is diamagnetic in nature. So hydrogen molecule is diamagnetic in nature. Next molecule, helium, He2. You know, atomic number of helium is 2. Then here 2 helium atoms are combined to form helium molecule. So 2 plus 2, total 4 electrons. Then electronic configuration is sigma 1s 2, sigma star 1s2. This is bonding molecular orbital of 1s and this is anti-bonding molecular orbital of 1s. So 1s atomic orbital of one atom combined with another 1s atomic orbital of other atom, then we get 2 molecular orbitals. One is sigma 1s and other is sigma star 1s. That is, this is bonding molecular orbital, this is anti-bonding molecular orbital. So this bonding molecular orbital consists of 2 electrons and anti-bonding molecular orbital also consists of 2 electrons because we have 4 electrons in our hand. This is the electronic configuration. Then bond order is equal to Nb minus Na by 2. Here the number of electrons in bonding molecular orbital is 2 and the anti-bonding molecular orbital means star is there. This is anti-bonding molecular orbital. This also have 2 electrons. So 2 minus 2 divided by 2, which is equal to 0. That means He2 molecule is therefore unstable and does not exist. Next, lithium molecule, Li2. You know, lithium atomic number 3. Then total 2 lithium atoms are combined. So 3 plus 3, 6 electrons are present. Then the electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2. Because in our hand 6 electrons are only. So these are occupied in the each molecular orbital 2 electrons are accommodated, similar to that of atomic orbitals. The above configuration can be also written as, this is K shell, main shell, sigma 1s and sigma star 1s is K main shell. So this sigma 1s2 and sigma star 1s2 can be equivalent to KK. That means closed K shell structure. That means these are completely filled K shell. So we can easily written as, instead of sigma 1s2 and sigma star 1s2, we can write KK. Indicate closed K shell. That means completely filled K shell. Then the remaining only sigma 2s2. Then the bond order is equal to Nb minus Na divided by 2, which is equal to, here the number of bonding electrons are here 2. Here also bonding molecular orbital 2. 2 plus 2, 4 electrons minus anti-bonding. The star is there. This is anti-bonding molecular orbital 2 electrons. So 4 minus 2 divided by 2, which is equal to 1 electron. It means that Li2 molecule is stable and there is no unpaired electrons. All electrons are paired. 2, 2, 2. All electrons are paired in the molecular orbitals. So these are diamagnetic in nature. Then the next one is beryllium molecule. Atomic number 4. Then consists of 2 beryllium atoms. So total 8 electrons. Electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. This instead of the sigma 1s2 and sigma star 1s2 we can write kk, closed K shell. Then the remaining is sigma 2s2, sigma star 2s2. Then the bond order is equal to Nb minus Na by 2. Nb, number of bonding electron is here 2 plus 2, 4 electrons. Then the anti-bonding star is there. So this 2, here star is there, anti-bonding 2, total 4 electrons. So 4 minus 4 by 2 which is equal to 0. That means Be2 molecule cannot exist. Next one is boron molecule, B2. Boron atomic number 5. So total number of electrons 5 plus 5, 10 electrons. Electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Pi 2px is equal to pi 2py. Consists of here 2 plus 2 plus 2 plus 2, total 8 electrons are over, remaining in our hand 2 electrons, but our molecular orbital is pi 2px is equal to pi 2py. These both having same energy, degenerate molecular orbitals. So in our hand 2 electrons, according to Hund's rule, first singly filled, then only pairing up takes place. So we given 1 to this 2px molecular orbital and 1 to 2py molecular orbitals. So this can be also written as kk. Kk sigma 2s2, sigma star 2s2, pi 2px is 1, pi is equal to pi 2py 1. Bond order is equal to Nb minus Na by 2. Nb, number of bonding electrons are 2, 4, 5, 6. 6 minus 2 plus 2, 4 by 2. 6 minus 4 by 2 which is equal to 1. So it is a stable molecule with the 2 unpaired electrons. 2 unpaired electrons, not this. 2 unpaired electrons are present in pi 2px is equal to pi 2py molecular orbital. So this is paramagnetic in nature. This is not pair up electrons, this is unpaired electrons. So this is paramagnetic in nature. Next one, carbon molecule. Carbon atomic number 6. Then total 12 electrons are there, 6 plus 6. Electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Pi 2px is equal to pi 2py. In our hand, 4 electrons are there. 2 electron is given to pi 2px and 2 electron is given to pi 2py. Then otherwise written as kk, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py2. Bond order is equal to Nb minus Na by 2. Nb 2, 4, 6, 8. 8 electrons. Antibonding molecular orbital containing 2 plus 2, 4 electrons. 8 minus 4 by 2 which is equal to 2. So the molecule is stable and diamagnetic because it's having a positive value, bond order positive value, then the molecule is stable with the diamagnetic nature because all electrons are paired electrons, 2 electrons. Okay. Next one, nitrogen molecule. You know nitrogen atomic number 7. So total 7 plus 7, 14 electrons. Then electronic configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 is equal to pi 2py. Then sigma 2pz2. Then we can write the bond order is equal to, here number of bonding electrons are 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. 10 minus anti-bonding molecular orbital containing electrons 2 plus 2 4 divided by 2 which is equal to 3. So we know in nitrogen N triple bond N is present. Bond order 3 means N triple bond N. This is a stable molecule and diamagnetic. All electrons are paired electrons. So it is diamagnetic in nature. Next one, oxygen molecule. Oxygen atomic number 8. Total 16 electrons are present in oxygen molecule because 8 plus 8. 2 oxygen atoms are there. Electronic configuration is, in the case of oxygen and fluorine, a small exception is there. First sigma 2pz is coming, then only pi 2px is equal to pi 2py coming, because this is less energy compared to this one. So electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, then pi 2px is equal to pi 2py, both consist of 2 electrons. Then remaining in our hand 2 electrons are there. The next molecular orbital is pi star 2px is equal to pi star 2py. So both having same energy. So we give 1 electron each of these 2 molecular orbitals. So bond order is equal to Nb minus Na by 2. Nb, number of bonding electrons are 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. 10 minus antibonding 2 plus 2 plus 1 plus 1, which is equal to 6. 10 minus 6 by 2, which is equal to 2. That is the molecule between oxygen molecule a double bond is present, that is bond order 2. The molecule is stable and paramagnetic because due to the presence of unpaired electrons in the antibonding molecular orbitals. This molecular orbital consists of unpaired electrons, so it is paramagnetic in nature. Prove oxygen molecule is paramagnetic, then you should write the electronic configuration. Then this molecular orbital consists of unpaired electrons, so it is paramagnetic in nature. Then the next one is fluorine molecule. Fluorine atomic number 9. Then total 18 electrons are there. Electronic configuration sigma 1s 2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2. Then pi 2px is equal to pi 2py. Each consists of 2 electrons. Then pi star 2px is equal to pi star 2py. Each consists of 2 electrons. Total 18 electrons. Then bond order is equal to Nb minus Na by 2, which is equal to 2, 4, 6, 8, 10. 10 minus 2, 4, 6, 8. 8 divided by 2, then which is equal to 1. So from this, in between fluorine molecule on single bond is present. Molecule is stable and diamagnetic due to the presence of these paired electrons. All electrons are paired. Next our portion is hydrogen bonding. It is defined as the attractive force which binds the hydrogen atom of one molecule with the electronegative atoms such as oxygen, fluorine, nitrogen, etc. of another atom. For example, you know HF molecule, hydrogen fluoride molecule. In between them, a single covalent bond is present. This fluorine atom is more electronegative than hydrogen. So these two electrons are attracted towards this fluorine atom. So this end become partial negative and this end become partial positive. Similarly, this is another molecule HF. Then these two electrons are attracted towards fluorine atom. This end become partial negative and this end become partial positive. So here you can see this end is negative and this end is positive. So these two opposite ends are attracted to each other. Attracted to each other. This attraction is indicated by dotted lines. This bond is known as hydrogen bonding. This is not a covalent or ionic bonding. This is just a force of attraction between hydrogen and the most electronegative elements such as oxygen, fluorine, nitrogen, etc. Similarly, here also another HF molecule we consider. Then this end become partial negative negative and this end become partial positive. This negative end attract the positive end of another molecule. This attraction is known as hydrogen bonding. Types of hydrogen bonds, these are of two types. Intermolecular hydrogen bonding. It is formed between two molecules. Similarly, in the case of HF molecule, different HF molecule we consider, then between them the hydrogen bonding is present, which may be same or different. Here HF molecule, same HF molecule, in between them hydrogen bonding is present, then they are known as intermolecular hydrogen bonding. Next one is intramolecular hydrogen bonding. That is, the hydrogen bonding is present within the molecule is known as intramolecular hydrogen bonding. Example, orthonitrophenol. This is orthonitrophenol. This is benzene ring with OH is known as phenol. Then in the ortho position, next adjacent position is known as ortho position. In this position a nitro group is present, so it is known as orthonitrophenol. Orthonitrophenol can be write like this benzene ring with OH, and nitro group can be written as N double bond O single bond O, NO2, N double bond O single bond O. So in between this hydrogen and one oxygen there is a force of attraction is exist. That bonding is known as, here this dotted line indicating hydrogen bonding. So within one molecule the bonding is present, then it is known as intramolecular hydrogen bonding, and between the molecules it is known as intermolecular hydrogen bonding.